So most of the vegetables in WA, they are grown in sandy soils and, think beach sand. So when the growers apply water and fertilizers, 50 to 60% of the water and the nutrients, they leach beyond the root zone. So that's not being utilized by the plants.
Welcome back to the Vegalogue podcast, a dialogue about the Australian vegetable industry from AUSVEG. I'm Tom Bicknell. The deep sandy soils of Western Australia's Swan Coastal Plain are among the most infertile in the world. They're also where many of the state's vegetables are produced, however, and growers have long struggled with the low ability of these soils to retain nutrients or moisture. More than 60% of irrigation water and nitrogen fertiliser applied to vegetables in the sandy soils of the Swan Coastal Plain leach past the root zone. The story is not much better for phosphorus or potassium. Against that backdrop, input costs have continued to grow, water allocations tighten, and concerns about fertiliser runoff into waterways and wetlands increase. In an effort to address this problem, WA's Department of Primary Industries and Regional Development has launched a new levy-funded project to develop a system for capturing leached nutrients and water from below the crop's root zone, recycling this water back onto the crops as irrigation. The project, which runs until February 2030, will investigate the use of geomembranes installed below the root zone of crops to collect leachate and divert it into dams for reuse. I had a chat with DPIRD research scientist Dr. Valeria Almeida Lima about the project and how this new system might work. Thanks very much for joining me, Valeria. To start off with, could you maybe explain the challenge that vegetable growers are facing in WA's sandy soils and describe maybe the soils that we're talking about here?
So it started when I started with DPIRD in the southwest region. So I'm based in Bunbury. And one of the issues that we were trying to help the growers with, or the challenges, was how to minimize leaching of water and nutrients below the root zones in the sandy soils. So most of the vegetables in WA, they are grown in sandy soils. And we're talking about sandy soils with, like a typical 2% clay content. So it's, think beach sand, so structureless, and so that's the main challenge. So when the growers apply water and fertilizers, from past trials, we see that over like 50 to 60% of the water and the nutrients, they leach beyond the root zone. So that's not being utilized by the plants. So that requires like a loss for the farmer because you can't really recover that. It's passed beyond the root zone. So that was the main challenge. So the department has worked for many years on helping growers try to improve the water use efficiency for irrigation. You apply, water based on the plant demand and minimizing that leaching, only applying based on what is required. But given the nature of the soils, that poses a challenge, especially when the growers have crops growing in different phases. One that you've just transplanted to the one that you nearly harvested, they have, of course, different crop factors that require different amounts of irrigation. So it's hard for them when they have one system installed in the farm. So that poses a bit of challenges. So, and especially with fertilizers like nitrate leaches very easily. So those was the two main challenges. So water and fertilizer leaching in the sandy soils. Another challenge for these soils is because given the nature of it is just low in clay content, around 2%. Some growers, they are working on increasing the clay content of the soils to improve water and fertilizer retention, but it's not widespread. We do have researchers working on that area, identifying some of the good amendments that we can add to the soil to increase that retention of nutrients and water. So we're working on different fronts. But then we came to the challenge that I proposed. My supervisor was like, what if we just collect everything? We're having a hard time trying to make sure we apply frequent and slow and, the quantities. And it's very hard. We've been working years and years. So what if we just collect everything and then we recycle it? that would might help the growers, and it would take that pressure of just be monitoring it on the clock and make sure nothing leach, especially if you are in some areas there are sensitive aquatic environments where horticulture has been limited and they not, the amount of fertilizer you're allowed to apply annually really limits the activity. So those were some of the areas that also we wanted to propose a technology that will allow in future those areas to be developed. And then it sounded like a crazy idea, but it's been probably 3 or 4 years on the making this idea before this project was approved. So we were very happy. It sounded like a big idea, but then you start researching, and then people were doing so drainage is done for a different reason most of the time, to remove the excess of water from the paddock. So it's been done, in a lot of countries, and those were the fields that we're trying to learn from. So it's technically possible. It's just we're applying for a different purpose. It's for the opposite purpose, but ends up the same technology. The tools that we are using, it's similar.
So could you maybe just give us the elevator pitch of what the technology is and how it works? Like physically, what's this going to do in the field?
So the way we envision it is, so drainage pipes. The challenge with a drainage system design is how deep you place your collecting pipes, and how far apart you place them. So that's what we're hoping to design with the help of some modeling. So the system would be, because normally when you drain, you have an impermeable layer, or could be like a clay layer that would prevent water going deep down the profile, so that will accumulate and build up. In our case, because we've got sandy soils, we have to install an impermeable layer, depending on what we decide is going to be the best depth for our soils. But you're going to remove a deep layer of soil, place an impermeable layer with like a geotextile membrane. We're going to test different materials, so we don't know which material exactly it's going to be. And there are new technologies they use for drainage nowadays. For sport grounds, there's a couple of materials that we're going to look at, the ones that make it easier for installation. That's the first part, determining the depth of the layer, and then installing that impermeable layer, because to collect it, you need to stop it. And then above the impermeable layer, we're going to have the actual drainage system, which are pipes and with a bit of a slope to allow water to run. And then you have lateral pipes draining into a collecting gutter pipe, and that's going to be taken out of the field. And the reservoir will depend if the property already has a dam, then we can redirect that water to the existing dam, or then we can calculate how much of a reservoir you need for that system, and then we recycle that water back as irrigation. That's the whole idea of the system. So the ins and outs and the technical features of it, but it's yet to be determined during the project.
So you say the kind of drainage system you're talking about has been used elsewhere, as you say, for areas with too much water. The approach with putting an impermeable layer under the ground, has that been done elsewhere before?
It has been done to some extent. Like we see the Michigan State University in the US, they do have a system where they install polyethylene membranes under the root zone, but they don't do it across the whole area, but they do create a limited area of impermeable layers on the subsoil, and then they cultivate on top. So it's more like creating pockets of water reserve under the root zone. So they have developed a machine for that. And they have seen increase in yield for corn and increased in water content where the membrane was placed. So that was gaps in between the membranes. It's just like little pockets, how they do it. There's also, in the literature, the early days, they use like asphalt on the trees as well. So it has been done, but not. And the sandy soil poses a different challenge because you don't have lateral movement of water. The water runs straight down. If you had drip irrigation, you could place the plastic right underneath the row where the drip goes. But when you have overhead sprinklers, that's another challenge, because where do you capture the water? And then if you move your row in places between seasons, then it poses a different challenge. So that's why we thought, okay, let's do the whole area to try it out. But we're hoping in future this technology can be adapted to different places and different, cultivating methods that use drip irrigation. Then, yeah, you can modify that. That's our hope in the future.
I guess this could essentially be described as in-ground hydroponics. What's the benefit over open hydroponics or bag culture systems?
Yes, exactly. That's a simple way to describe it. And when you look, how many times the water can be recycled in hydroponics are very high, and they have been doing it for a while. And given the nature of our sandy soils, we're hoping that it's going to be a similar system, and that's what we're going to find out.
So I guess the difference over bag culture systems, where they put plastic bags filled with a growing medium on top of the ground and then irrigate those, is the difference. You're growing in soil, so you've got all of the soil biology as opposed to a fairly sterile growing medium. Does this kind of system, do you think it will have much of an impact on soil biology?
That's one of the things we're going to look at. But one of the aims of this system is, when you design the system, you have to make sure you consider first the sensitivity of the crop you're cultivating to water, to soil wetness, and you design your system in a way that you're removing that water from the soil as quickly as possible and at the rate required, so you're not waterlogging your root zone, because you don't want damage that the microbiology of your soil. You don't want to damage the root zone, and you don't want your plants to reduce in yield because they are waterlogged situation. And because we hoping to apply in such a depth, like let's say 70 centimeters to a meter, that's sort of what we have in mind. So the majority of the soil will be under unsaturated conditions. So we will definitely monitor the impacts on the soil microbiology and the plant response to that. That's one of the aims of having this project, is to have the opportunity to assess those before we roll the technology out. But yeah, we've definitely looked into that. But one of the aims is to preserve that, not to have any impact.
Talking about the depth of about 70 centimetres to a metre, is that likely to cause any problems for crops that require a bit more soil disturbance, like root crops, for instance?
We don't expect it to pose any problems, given the depth. If you look into the soils that would require a bit of more disturbance for harvest, for example, for potatoes and so forth, we hope that you'll be in a depth that it won't be impacted by it.
And are you envisaging this as being a permanent installation, or something that's replaced every year or two, like plastic mulch, for instance?
No, we don't. We're hoping that we can have, if you look at conventional drainage system, they will last, 15 to 20, 30 years. So we're hoping that it's a fairly permanent system, that you don't need to replace it every season, given the disturbance of the soil to remove layer. And some of the technologies for the geomembrane they have, you have the option to detect leaks into it. So if that happened, you have the chance to locate it and just fix it on this spot that is actually causing problems, rather than removing the whole thing.
And this is a fairly long-term project, I think a bit over 5 years. What are the stages that you'll be working through?
So it's divided in 3 stages. On the first stage, we're hoping to tackle the design of the drainage system, and that we're going to use like computational modeling tools, softwares. One of them is like Drain Mode, and then there's Hydras, where we're hoping to, we're going to design the drainage system, and then some of the models, they have the capacity to simulate the yield of the crop that you're going to have, the quality of the water in terms of salinity, nitrogen recovery, so those figures. So in the first year, that's what we'll be mainly doing, focusing on designing the system. The second stage, it's on the second and third year. That's when we're going to deploy a pilot scale. and that we're going to really have numbers quantified, the improvements in water use efficiency, fertilizer use efficiency, the microbiological and chemical composition of the water and how safe it is, and in terms of guidelines. That's the main thing for the pilot scale. There is a stop and go milestone after year 3, and that's when, given also we want to check the economic feasibility of the system. So given the complexity of it and the cost involved, the upfront cost. So after we've assessed all of that through the pilot scale in years 2 and 3, we're going to assess, is this worth going ahead to a larger area? And then that's when we're going to do in year 4 and year 5, extend it to a farm trial to a larger area.
Well, thank you very much for the chat, Valeria. I look forward to watching the project develop.
My pleasure.
The Evaluating On-Farm Water and Nutrient Recapture in Western Australian Production Systems project is funded by Hort Innovation using the Frontiers Fund and contributions from the Australian Government under project code AS23009. If you'd like to learn more about the project, there'll be a link in the episode description to the listing on the AUSVEG Knowledge Hub, as well as Dr. Lima's contact details. You've been listening to the Vegalogue podcast. Don't forget to subscribe and give the podcast a rating and review. Vegalogue is produced by AUSVEG, the peak industry body for Australian vegetable growers. You can find more news and information from AUSVEG at ausveg.com.au, on our social media channels, or in Australian Grower magazine. See you next time.